So in this video, I just want to introduce some of the notation that's common with using integrals. And this is what's known as sigma notation. So this is used basically whenever you're summing anything. So when you're adding a bunch of things together. So again, this is the idea that we're going to explore of taking all of the rectangles underneath the curve, finding the area of all of them, and adding them all together. Right, so we're going to be doing some kind of summing. So, in general, if we wanted to write that we want to do 1 plus 2 plus 3, and we want to go all the way up to 20, say, then of course it would be very cumbersome to write out every single number. Even writing out like this, it could definitely be a little more compact. So we use what's called the sigma notation. So the sigma notation would look something like this. So it's named this because we have the Greek letter sigma, which just kind of looks like an E. Let me try to draw it a little better. It's flat on the top, and then it comes down like this, and it's flat on the bottom. Okay. So you could just look up the Greek letter sigma, and this is the capital version of it. The lowercase version of it is usually used for standard deviation in statistics, of course. So you might already be familiar with this notation, from other stats classes or whatever, but I'm just going over it just in case it's new. So if we wanted to write something like this, what we would do is we would write the index at the bottom that we want to start with. So we often use I for the index. And the index means that usually we just use this to denote which variable we're talking about. It doesn't usually have physical meaning, but it can, like numeric meaning, but it can, like it will right here. And then we write whatever the last number we want on the top. So in this case, maybe we write I equals 1 to 20 of I. Okay. So what this is telling us to do is to plug in I equals 1 for the first number, and then I equals 2 for the second number. And the sigma itself means to add all of these terms together. And then I equals 3 for the next number. And then you just keep doing this until you get to the last number, which is listed on top, which is 20. Okay. Now, more generally, like I said, the index doesn't always have physical meaning. We might write instead something like this, where we have A sub I, and then maybe we go I equals 1 to N. And what this means is that we want to add together the terms A1 plus A2 all the way up to A sub N, whatever N is. Maybe we don't even specify it. Maybe we just want a general formula. But in general, here the I's don't really have any numeric meaning. They're just indexing the variables, meaning they're just giving them names, right, to distinguish them from one another. So A1 and A2 and A3, they might not have any kind of relationship. They are just, different variables. So you see this a lot in statistics when you're talking about your data, right? You index your data as X1, X2, X3, and that just means the first data point, the second data point, the third data point, and there might not be any relation there. So the 1 and the 2 and the 3, they don't have any numeric meaning. They're just being used for names. Okay. So if we had something like, if we were given something like I equals 1 to 5 of 3 to the I, for example, then this would tell us that we're doing 3 to the 1 plus 3 to the 2 plus 3 to the 3, 3 to the 4 plus 3 to the 5. Okay. So the sigma notation only goes over the positive integers, or sometimes 0 can be included in this. You can even have negative numbers included if you make your bottom index negative, but we don't typically see that too often. But it doesn't, have any of the decimal place. Like we're not doing a 1.5 place or 1.7 place or anything like that, right? So we're just looking at the integers essentially. So we would do this. You could add these together. You should get 363. Or maybe we're given the sum 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 right? And maybe we want to now write this in a more compact notation using the sigma notation. So we would look for a pattern here to see how we would do that. So in this case, maybe I'll use n for the index, because that's also common to do that way. And then again, we have 5 terms. And what's going on here is that we're doing 1 over n squared. Okay. So you can do this backwards. You'll see 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, etc. Okay. So you're generally just looking for the pattern though. So we'll explore this notation a little bit more because the last third of the class is dedicated to sequences and series. This is an example of a series right here, and particularly infinite series. So our upper index number is infinity, right? So we'll explore this more then. Here we just really need the basics to start talking about the sums of the rectangles associated with integration.